4, I will explain BERT, and in lecture 5, I will explain how to implement BERT from scratch using PyTorch implementation. And lecture 6, I will explain how to use BERT. But before going to lecture 4 and 5 and 6, we have part 2 and part 3, which are some ideas like ELMO in the next lecture and ULMFiT in the present lecture. You will see the reason that I explain these papers because you should see the evolution of ideas, why something like BERT appears. And when you learn the process, then you understand why some ideas appears and evolves, and then you can even predict what is the next idea. Because all of them is just a pattern that researchers are involved in. A good process, an important process inspired by transfer learning is, first you have, for example, a large corpus, a language model, and you fine-tune it using task-specific data set, for example, a question-answering data set. And then you test it. So sometimes, for example, this process in BERT or anything else is pre-training, and then we have fine-tuning, and then we test the results. So this is an important process. So I will explain this lecture, Universal Language Model Fine-Tuning for Text Classification, in 2018. And of course, there are other important papers like this one, Language Model are Unsupervised, Regularized, and Optimizing LSTM. So inductive transfer learning has greatly impacted computer vision, but existing approaches in NLP still require task-specific modifications and trainings from scratch. So we don't want to do from scratch everything. Whenever we have a new task, we want to do something like transfer learning, like continual learning, that we take advantage of something we have learned before. Just like human mind. For example, my niece is a 4-year-old. She never starts learning from scratch. She continues what she has learned and builds upon it. And so it's just, it's like transfer learning. So in this paper, they proposed ULMFiT, which is Universal Language Model Fine-Tuning. You can apply to any task. And they introduced techniques that are key for fine-tuning a language model. So you know language model from last lecture. So the contributions of their paper is that they propose that to achieve computer vision-like transfer learning. They propose discriminative fine-tuning, slanted triangle learning rates. I mean, for example, you change the learning rate gradually, and gradual unfreezing. Unfreezing is very important in all paradigms. You talk about it in continual learning, transfer learning, algorithms, so it's very important. And there are other contributions. So they propose this algorithm which pre-trains a language model on a large general domain corpus. As I said, first we start with a large domain because we are at the stage of pre-training. And then fine-tune it on the target task. For example, we have a different small vocabulary and text, but there are something new that has not been seen in the, for example, maybe we have not ever seen it in the even the big corpus, or we want to do domain adaptation or something like that. So in our experiments, they use LSTM. It's a kind of LSTM, AWD. And so consists of the first a general domain language model pre-training, and then a target task language model fine-tuning, and the third step is target task classifier fine-tuning. So, for example, for the pre-training, as I said, the first step is pre-training. They go the embedding layer, just like every time we do embedding from word to vectors, from integers to vectors. And then there are a couple of layers, and finally we have a softmax layer. By the way, in the lecture 7 or 8, I will explain hierarchical softmax. Because what if the size of your vocabulary is really huge? You don't want to normalize, and it takes a lot of time. As you have seen, the hierarchical softmax can be used for in language modeling like this. It can also be used in word2vec. You know, in word2vec has two problems, and if you watch my playlist for word2vec, I explained negative sampling and hierarchical softmax. So instead of softmax, in future people will use hierarchical softmax because it's very fast. It doesn't need doesn't have the problem of this softmax that you need to normalize over a large size vocabulary. So it takes time, and it's very beautiful. If you love Huffman code and those things in computer science, then you should definitely learn hierarchical softmax and use hierarchical softmax for almost all of your projects, because in future you will see everything is about hierarchical softmax. They don't use softmax anymore. And so this is the pre-training. So we learn by layers. There are some layers. So the first layer is essential, the second layer is less essential, and the third layer is less than less essential. So these are important because when you want to do your unfreezing, it's very important, and you should know what is continual learning, what is transfer learning, to appreciate this paper. Then the second step, like any other algorithm, like BERT that I will explain, is fine-tuning. So you should fine-tune language model, and so everything is the same, but you do on a different corpus, probably a small corpus. And the third step, which is just a task. It could be a classifier, for example, fine-tuning. For example, a different task. So we don't have ImageNet in NLP, and ImageNet is for computer vision, but an ImageNet-like corpus for language should be very large. And we don't have that's why they created Leaky Text. They pre-trained the language model on Leaky Text, and it has 28,000 pre-processed Wikipedia articles and 100 million words. So it's quite large. It's good for pre-training. So pre-training is the most beneficial for tasks with a small data sets and enable generalization even with 100 labeled examples. The second step, as I said, is fine-tuning. So no matter how diverse the general domain data used for pre-training, the data of the target task will likely come from a different distribution. As I said, it could be totally different words, different text. So we thus fine-tuning the language model on the data of the target task. So given a pre-trained general domain language model, this stage converges faster as it only needs to adapt, domain adaptation, adapt to the idiosyncrasies of target data, and it allows us to train a robust language model, even for small datasets. We propose discriminative fine-tuning and a slanted triangular learning rate for fine-tuning the language model. So the third step is classifier fine-tuning. So finally, we should do fine-tuning, and we do it for a classification. For fine-tuning, we augment the pre-trained language model with 2 additional linear blocks. So you have hidden dimension, and you map it with linear layer to your vocabulary size, or here, or your classifier, for example, 2-thing classifier. For example, is it next sentence? Is it not next sentence? Just like BERT that we do it. I will explain BERT in lecture 4 and 5 and 6. So here we are just doing classifier. And of course, they use batch normalization and dropout with ReLU activation and softmax activation. We will see hierarchical softmax in future years, and that outputs the probability distribution over target classes at the last layer. Note that the parameters in the task-specific classifier layers are the only ones that are learned from scratch. The first linear layer takes as the input the pool last hidden layer states. So in classifier fine-tuning, if you can just concatenate the last time step, hidden state at the last time with the max pool and also mean pool. So if you concatenate 3 different vectors, then you get this vector. So this is what we say by concat pooling, because we combine the information of max pooling, mean pooling. So because if you just use the last time step of h of t of the document, if you just use the last hidden state of the last time step, it doesn't have the context of the document. You cannot represent it. So that's why we need a more complex information. And gradual unfreezing, this is very important. So we first unfreeze the last layer, because the last layer is not important. It's very shallow things. You can even ignore that. It is just like in human brain. In the last layer, it's something that maybe you have learned it today or yesterday. And fine-tune all unfrozen layers for one epoch. And then if unfreeze the next lower, so we start from the last layer. For example, in BERT is layer 12. Then we go to layer 11, and then you go to layer 1. For example, in BERT we have 12 layers. And that's it.